Okay, so let me try to share my screen. Okay, can you see my screen and notes?
Yes.
Okay, perfect. So let's start. So welcome everyone to our next lecture on root locus. And before we start with today's lecture, I would like to make a brief summary of what we have been talking about. So in our previous lecture, we said that we would like to consider a standard feedback loop. And we said that, okay, in that standard feedback loop, we defined the open loop transfer function, which is g of s, h of s, and the closed loop transfer function, which is equal to g of s divided by 1 plus g of s, h of s. And once again, we said that, okay, the denominator of the closed loop transfer function is very important. We are interested in the closed loop poles. And at a certain stage, we said that, okay, assume that we have our open loop transfer function is given as k times n of s over d of s. So there's a parameter k, which is a free parameter that I can change, let's say from 0 to infinity. And what I would like to inspect is then what happens to the closed loop pole positions as I change k from 0 to infinity, okay? So for example, in the Roth-Hurwitz method, my question was simpler. So how many poles are there to the left or right of the imaginary axis when I change a parameter or something, given a polynomial? But in the root locus, I was more interested in the trajectory that is followed by the closed poles. For example, here is our first example. There was a second order system, and the poles start at -2 and 0 for this example when k is equal to 0. And when I increase k further, I end up with complex conjugate poles, and which is moving on this line over there. So, and I was looking for this trajectory, and I wanted to find, I wanted to sketch the closed loop poles trajectories, the locations when I'm changing the single parameter. Okay, so here is the brief definition of the root locus: the trajectory followed by root locations. What we're interested in most of the time is closed loop poles when a single parameter is changed continuously, and that single parameter is usually indicated by k in our example. Okay. And we said that to attack such problem, I need to write down the denominator of the closed loop transfer function, like 1 plus g of s, h of s equals 0. So that's what I'm interested in. And what I'm interested in, that being equal to 0 implies that g of s, h of s is equal to -1, right? And we said that in the complex domain, this indicates two things. So first of all, the magnitude of both sides of the equation should be equal to each other, and the angle of both sides of the equations should be equal to each other, right? So I can write any complex number and its magnitude times its and e to the j power to its angle, and then these two should be the same on the left-hand side and the right-hand side of the equations. And we said that, okay, we can inspect these equations when we are given g of s, h of s as k times n of s, d of s, okay? So we are pretty much dealing with the same equations all the time, right? G of s, h of s is equal to -1, 1 plus k n of s, d of s is equals to 0. So I can also add, for example, this another one which I use very frequently. So notice that the closed loop transfer function, so 1 plus k n of s divided by d of s equals 0 has the same roots with d of s plus k times n of s equals 0, right? So this is my the denominator of the closed loop transfer function. So in a way, you can think about the root locus as I know the open loop zeros, which are the n of s here. I know the open loop poles, okay, d of s over here. What I would like to find is the roots of d of s plus k times n of s as k change from 0 to infinity. And in our example, as you remember, it was k, and I have 1 over s times s plus 2, right? This is n of s, and this was d of s. And we were looking for the roots of s squared plus 2s plus k. So d of s plus k times n of s. N of s is equal to 1 here, okay, in this example. So that's what we are sketching in the root locus. Anyhow, we said that, okay, so the something being equal to -1 means its magnitude is equal to 1 and its angle is equal to pi in the complex domain. We show those examples and then we try to write down these conditions explicitly. We said that, okay, let there be m open loop zeros in our open loop transfer function and n open loop poles in our open loop transfer function. So let's inspect what does this magnitude condition imply and what does this angle condition imply. And we were given an example here. So saying that, okay, suppose we are given a test point S and we would like to find if that test point S is included in the root locus or not. So if it is included in the root locus, that means by changing the value of k, I can bring the closed poles to that dedicated location, that chosen test point, okay? But if the selected point, that test point is not on the root locus, so for any value of k positive, I cannot bring the closed poles to that test point location, okay? So it has that kind of a meaning rather than inspecting random points on the if whether they exist on the root locus or not. Okay, so we have a purpose for that. And we said that simply implies that for this example, green point is our test point and I'm inspecting S minus Z1, this BAB, and S minus P1, that AE vector over here. So length of the magnitude condition implies that AB, AE, AD, AC is divided by those should be equal to 1. And the angle condition says that the angle of S minus Z1, which is psi 1, minus those three angles should be an odd multiple of pi. Okay, so this angle condition for the test point. So I would like to read out this remark to begin our today's lecture. So in this remark, I claim that only the angle condition determines if a test point S is included in the root locus. Once, this should be E, once a point satisfies the angle condition, the corresponding K value can be found using the magnitude condition, okay? So as I said, so if a point is on the root locus, that angle has to be a multiple of pi, okay? An odd multiple of pi. And you can find the corresponding K values if this second equation is satisfied by carrying out these lengths and find the corresponding K value, okay? So I can, for example, illustrate this in another example. So in a second or so, I will write down an example transfer function. I will try to plot the root locus for a general transfer function, okay? And while doing that, I will try to write down the rules that should be followed when sketching a root locus, okay? And I would like to combine one of these rules with these conditions over here, this angle condition, with this remark over here. It says that the angle condition determines if a test point S is included in the root locus. So I would like to show you that by inspecting the part of the real axis that is included in the root locus. Okay, so let me try to write it down. A second, please. So let me write down this as root locus on real axis. Okay. So if you remember our first example over there, so this part of the real line is not included on our root locus. That part of the real line is not included, but that part is included. So, and I will show that this wasn't a coincidence. That was because all these points satisfies the angle condition there. I will show that in a second. So that's my aim right now. So let me show you a simple example to illustrate my claim. So let me sketch down something like this. Let this be the S-plane, and suppose I have the open loop zeros here, let's say at +1, Z1 is equal to 1, okay? And suppose I have open loop poles, P1 is equal to -2, and this is P3 is equal to -3, let's say, okay? And once again, just like I did over here, I would like to pick a test point on the real line at different sections of the real line, and I want to inspect if that can be included on the root locus or not. Okay, And what I will do first is that I will select my test point as to the right of this 0 over there, okay? And so the vectors that I'm interested in is that the S minus Z1, S minus P1, and S minus P3, right? So let me plot those vectors. So this is my S minus Z1 vector over there, okay? And this is S minus P1. So this should be on the real line, but that will cloud the my sketch. So that will ruin my sketch. That will come on top of each other. I don't want that. And the last vector is going to be actually this vector, but I will plot it over top here. And this is S minus P3 vector, okay? And what are the conditions that I need to have for the angle condition, okay? So let me apply. So when my test point S is greater than 1, I would like to write down the angle condition. So the angle condition, since this is the 0, it should be, what I'm writing down is this equation, okay? So what I'm trying to write down this equation for this example. So I will sum up the angle of zeros and subtract the angle of poles up there, okay? Okay, so angle of S minus Z1 is equal to minus, let me continue, angle of S minus P1 and minus angle of S minus P2 should be an odd number of pi. Okay, odd multiple of pi. So it is 2k plus 1 times pi for k is equal to 0 plus minus 1, etc. Okay. So what is the angle of this first vector here when S is to the right of this Z1? What is the angle of S minus Z1?
0.
Exactly, so this is 0, right? And what is the angle of S minus P1? That is the same, again 0. And the angle of S minus P3 is again 0, right? So 0 minus 0 minus 0 is equal to 0. And 0 is not an odd multiple of pi, right? It cannot be pi, 3 pi, 5 pi, etc. Okay? So it is not equal to 2k plus 1 pi. Okay, so which means that any test point to the right of this Z1, 0 over here, cannot be included on the root locus because those points on the real line does not satisfy the angle condition. Okay. So let's pick another test point then. Okay, so let me try to pick another S. Oh, by the way, this will be a bit difficult for me, so I will try to delete those if I can. Maybe I cannot. Anyways. Okay, so and 1. All right, so and this was my 0 back in there. And what I would like to do is to pick another test point between -2 and 1. Okay, so I will pick my next test point S. Okay, so between -2 and 1. Okay. And the vectors that I'm going to study this time is that the first vector is going to be the S minus Z1. So it is that vector, right? And S minus P1, okay, that vector like that. And S minus P3, that vector right there. Okay. So what is the angle of S minus 1 here, S minus Z1, in this example?
This time it is pi.
Exactly. So this time it is equal to pi. Okay. So and this vector has angle 0 and that vector has an angle 0. So I will subtract 0 and 0, so the angle to the poles over there. And that is indeed an odd number of pi, okay? So all the test points, okay, between -2 and 1 is included on the root locus, okay? So if I pick any point there, I can, all these points on the real line will satisfy the angle condition. How am I going to find the corresponding k? So I will study the length of these vectors, right? And then I can find the corresponding k value by using the length of these vectors and applying the magnitude condition. Okay, so the angle condition simply states that which part of the real line is included in the root locus or not. Okay, and I would like to write that as a rule. So 1 second. Okay, so this is equal to pi, and so I will, for the time being, get rid of these parts. Okay. And pick another test point, okay, something like that. So once again, if you continue, if you pick this point, let's say, okay, so S is between -3 and -2, okay. So the vectors that I will be interested in simply is going to be S minus that one and S minus P1, that vector, sorry, and S minus P3. So that vector, okay. And the angle of S minus that one is equal to pi, okay, minus angle of S minus P1, that small vector over is again pi. And S minus P3 is equal to, angle of S minus P3 is equal to 0. So that's again 0, and that's not equal to an odd number of pi once again. Okay. Okay. And if you do the same for the test points over here, you will see that these parts are included in the root locus. So let me try to plot it down. So I will get rid of these simply, okay. So the points between -3 and -2 didn't satisfy the angle condition, but if you write down the equations for the points less than -3, they will satisfy the equation. And this is because a point in the real axis is included in the root locus if the number of open loop poles and zeros to the right of it is an odd number, okay? So if I would like to plot that, so we tried test points here. These test points didn't work out. They weren't included in the root locus. We tried test points between -2 and 1. They were included. So this part of the real axis is included in our root locus, okay? And we tried these test points between -3 and -2. Those were not included in the root locus. But if you try test points less than -3, they will be also included in the root locus. Okay, because a point in the real axis is included if to the right of the test point we have odd number of poles and zeros. And if you go back to our very first example, it was the same case here, right? So any test point on the right half plane in this example was not included in the root locus. All the points on the real line between -2 and 0 were included in the root locus, but the points less than -2 have 2 poles, so it's an even number, 2 poles or zeros to the right of them. Therefore, these parts were not included. And in this example, we have these sections included in the root locus. So I would like to write that down as a rule and continue with another example. So let me go to, okay, maybe on top of that, I can write down my rule before the example. So I would like to write that, sorry, I should select this layer. Okay. So I would like to write that down as a point on the real axis is included in the root locus if the number of open loop poles and open loop zeros to the right of it, to the right hand side of the point is an odd number. Okay. So we will solve many examples about that. So don't worry about this rule if it is lengthy, but it's saying a simple thing. But what I just wanted to emphasize is that by simply applying the angle condition, I can, for example, find the parts of the real axis included in the root locus. And that might be critical in my, for example, controller design, because maybe I want the positive real axis not to be included in the root locus because that makes the system unstable, right? So I would like to have, for example, rather there's some negative parts of the real axis included in the root locus to get my poles there and make the system stable. So in different cases, I might choose to do that. Okay. So do you have any questions, by the way? Any questions? You can also write in the chat window and I can check the chat window later on. Okay. So I will continue with our next example here. Okay, we are given a standard feedback loop over here with the forward path gain as g of s as ks times s plus 1, s plus 2, s plus 3, s plus 4. And we have a unity feedback where h of s is equal to 1. And what we are asked to do is to sketch the root locus. The root locus when k is changing from 0 to infinity. Okay.
Hocam bir şey sorabilir miyim?
From 0 to infinity. Yes, please.
Angle condition'ı sağlıyorsak magnitude condition'da direkt sağlanmış mı oluyor?
Or, if you go back to this example, so maybe I can do, let me try to do that. The thing is that, so what happened to our sketch over there? Okay, so we plot those vectors there, right? And they're all positive. And the magnitude condition is related with this length of these vectors, which are all positive, right? AB is positive, length of AC is positive, length of AE is positive. If this equation is satisfied, then I can find the corresponding K value from this equation, right? So remember that I was plotting those vectors, right? And I inspected their angle. And all of these vectors also have a length. And their length should satisfy the magnitude condition, right? And if I can find the K value, a positive K value for these lengths, then everything is going to be fine, right? So it will be satisfied. Perfect. So let's continue. I'm trying to explain the logic and trying to answer your question directly, okay? So that you can make up your own decision that will be better for you. So for these, all the length are positive, all the length of these vectors are positive, then I can find the corresponding K once the angle condition is satisfied for positive case, okay? All right, so let's go back to our example. So what is the open loop transfer function here? In the meantime, I can pick. So open loop transfer function is g of s h of s. Okay, and it is given in the form of, it is again k times, let me write it like this, k times s over s plus 1, s plus 2, s plus 3, and s plus 4. Sorry, s plus 4. And it is given in the form of k times n of s divided by d of s. Okay. And what I'm interested in is the closed transfer function, right? So what I would like to find is if you compute the closed transfer function, the denominator of that thing is going to be equal to d of s plus k times n of s equals to 0. Okay, I'm interested in the closed poles, which is given by the roots of this equation. Okay, or more specifically, I'm trying to find the pole, closed pole locations, the roots of s plus 1, s plus 2, s plus 3, s plus 4 times k times s. Okay. All right. So I will sketch the root locus for the closed poles and for this open loop transfer function given in the form of k times n of d of s. And I will do that by writing down the rules of sketching root locus, and I will try to explain them, each rule and why did we say that. Okay. So the first rule is the start and end points of the root locus. So I write it down as start and end points of the root locus. Okay, and I will say that the first rule claims that the root locus starts at open loop poles and when I mean by starts at, it means the k is equal to 0. Okay, so when k is equal to 0, and it ends at open loop zeros or infinity. Okay, zeros or infinity. And this is the case when k goes to infinity. Okay. And so why does the root locus starts from the open loop poles? So remember that given n of s and d of s, we are trying to find the solution to the equation d of s plus k times n of s equals 0. This is the that gives me the closed pole locations, right? And when k is equal to 0, what is the equation? It is d of s is equal to 0. So d of s equals to 0 is the equation for the open loop poles. Okay, so when k is equal to 0, closed loop poles simply are equal to, is found by simply equating d of s to 0, and that is the open loop poles. Okay, so if you remember our first example with the second order example, we start our root locus from 0 and minus 2 at the very first example. Okay, and as k goes to infinity, okay, so color. So as k goes to infinity, we are still looking for the solution to this equation, okay? But the numerator, the n of s term, is dominating right now. So if k goes to infinity, this d of s terms can be neglected, okay? And then you will be simply looking for the roots of this equation will be approximately equal to, not exactly, okay, but approximately equal to the open loop zeros, okay, as k goes to infinity. And some of them also will go to infinity. We will show that. We will be talking about asymptotes very, very soon. And some of the loops goes to the zeros. But if there are more poles than more zeros in your open loop transfer function, just like in this case, So out of these 4 roots, only one of them will go to the zeros. The remaining 3 will go to infinity. Okay, we will see that in a second. All right, so another rule, the second rule that we mentioned was the root locus on the real axis. So maybe I can show that as well. So root locus on the real axis is found by inspecting any test point and counting the number of poles or zeros to the right of it. Okay, so that's what we have shown at the beginning of the lecture. And another rule is that root locus is symmetric with respect to real axis. Okay. Real axis. Maybe I can show, by the way. So, by the way, you can see that all of these rules are applies to our very first example where we found the exact locations of the roots, right? So the parts that we have included in the real axis, some of the poles are going to the infinity. Since there are no zeros, all of the poles are going to the infinity. And the root locus is symmetric with respect to the real axis. And the reason is that, so we are trying to find the roots of d of s plus k times n of s equals 0, right? And if the all numbers are, so maybe I can write it down like this. So we are trying to find the roots of this equation. And if we study all these coefficients of this complex equation is real, okay, so we have real coefficient polynomials. And for the real coefficient polynomials, the roots appear, the complex roots appear as complex conjugate. So for real coefficient polynomials, if a complex number is a solution to that equation, its complex conjugate is also a solution of that equation. Okay, so which means that any point, if it is included in the root locus, then the point opposite to that point with respect to the real line is also included in the root locus, and this is valid for all these points, so which makes the root locus symmetric around the real axis. Okay. And also you can, another way of claiming that is that you can check the angle condition, right? So if a test point S is satisfying the angle condition, you can show that S conjugate, the complex conjugate of that test point, also satisfies the angle condition. Okay. So far, so good. Okay, so, and asymptotes, that is the next thing that we will investigate. So, but maybe before the asymptotes, I should show the results of applying the first 3 rules on our root locus. Okay, so let me try to sketch that a little bit. Or I will do that after the asymptotes, because then I will have to repeat the sketch once again. But so it is better to do it after the asymptotes. Okay, so let me explain the asymptotes. So these are the lines we call the lines which are followed by the root locus, as k goes to infinity, are called asymptotes, we call lines which are followed by the root locus as k goes to infinity, asymptotes, I should say. Okay. So let's try to find the asymptotes in this very example. So I'll write down the rule. So the number of asymptotes is equal to number of open loop poles minus number of open loop zeros. Okay. And in this example over here, so where we have the n of s, so I can write down as with the blue color over here. So we have the open loop transfer function as s over s plus 1, s plus 2, s plus 3, and s plus 4 over there. Okay, so when k increases, usually the s is also increases. Okay, and when s is increases, when s is a very big number, so we are saying that the poles are following to the lines that code an infinity, which make those s points very big numbers. This transfer function can be approximated as approximately 1 over s cube. Okay, so when s is too large, this polynomial behaves as 1 over s cube. Okay, when s is too large, too very, very, very big number. Okay, and that should also satisfy the angle condition if it's on the root locus. So if I write down the angle of that thing, so angle of 1 over s cube should be an odd number of pi. Okay, so it should be equal to pi times 2k plus 1. Okay, and that simply says that, so minus 3 times angle of s, it should be an odd number of pi, sorry, 2k plus 1. Okay, and for this example, when the difference is the degree of the denominator and degree of the numerator is equal to 3, okay, the angle of the asymptotes becomes, so when k is equal to 0, I have my first angle, it's the angle of s, let's say it's equal to theta 1, it will be equal to minus pi over 3, okay, and when k is equal to 1, the angle of s should be equal to pi. That's my second asymptote, the angle of the second asymptote. Okay. And when the k is equal to minus 1, the angle of s is equal to, so it's going to be minus 1. These are going to cancel each other. So it will be equal to pi over 3. Okay. So now I would like to write down the another rule for that. So
ikinci açı minus pi olmayacak mı?
K'yi ben şurada ilk önce 0 verdim. O zaman minus pi over p oldu. Sonra K'ye 1 verdim. Minus pi ile pi aynı oluyor ya hani şeyde kompleks.
Tamam, doğru. Pardon.
Eksi 180. Yok, doğru söylediniz, gayet doğru söylediniz. Yani bir sıkıntı yok. Tamam. Yeah. So angle of the first asymptote, I should say, of the first asymptote. I will get the first positive one, okay? I don't need to say the first, second, and third there, okay? But I will get the smallest positive one as the first asymptote for the time being, is equal to pi times, so pi divided by difference between n minus n, okay? And n is the order of the denominator, and m is the order of the numerator, okay? So this was 4 minus 1 was equal to 3. So angle of the first asymptote was equal to pi over 3. And what I mean by the first asymptote was that the first smallest positive one for the time being, okay? And the angle between the asymptotes, so as you see, the angle between asymptotes are 2 pi over 3 here, 2 pi over 3 here, and between those two, it is 2 pi over 3. So angle between the asymptotes, is equal to 2 pi divided by n minus m. Okay, so in our example, this was 2 pi over 3, and this was pi over 3. So when you're trying to sketch the root locus, you can first find the angle of the first asymptote from the first equation, pi over absolute value of n minus m. And then you can find the second, third, and fourth asymptotes by adding this angle, that amount of angle to do your first asymptote, right? Pi over 3 plus 2 pi over 3 gives you the pi. And if you add another 2 pi over 3, you will get minus pi over 3, okay? And I will write one more rule, and I will sketch the root locus for the example by applying all the rules, and all of these will be more evident once I sketch the root locus, okay? Then I will get your questions. So one more rule that I would like to write next is the intersection of the asymptotes. Intersection of asymptotes with the real axis. So we said that, okay, I know the angle of these asymptotes. They will look, one of them is pi over 3, one of them is minus pi over 3, one of them is pi. But I don't know where to pick this location on the S-plane, okay? So I would like to find that point, okay? And this is given by, this is sometimes called the centroid of the asymptotes, okay? It's sometimes called centroid, shown by sigma. That is equal to difference between the summation of poles I from 1 to n pi minus summation of zeros, open loop zeros, divided by n minus n. Okay. So be careful, there's no absolute value here. So it is n minus m, and this is summation of pi and summation of zeros over there. And let's try to compute that for our example. So in our example, sigma 0 is equal to, I will get the summation of poles over here. So my poles are at -1, -2, -3, and -4. Okay, so it will be equal to -1 plus -2 plus -3 plus -4. And I will subtract the summation of zeros. And my only zeros, the open loop zero, is at s is equal to 0. It's at the origin. It will be equal to 0. And divide that thing by 4 minus 1 degree of the denominator minus the degree of the numerator. Okay, number of open loop poles minus the number of open loop zeros. Okay, so that will be simply equal to minus 10 over 3. Okay. So now I have enough material to sketch my root locus. So let's do that all together by applying all the rules that I have written so far. So let this be my S-plane. All right. And I am giving the task that, okay, given this open loop transfer function k times s over s plus 1, s plus s plus s plus 3, I would like to plot the root locus, okay? So the first thing that I would like to do is that I need to write down that thing as k times n of s over d of s, because these will be my open loop zeros and open loop poles. And I will use them to find the start and end point of the root locus, okay? So let me first place the zeros and poles on the S-plane, okay? So I have a 0 at the origin. So this is my 0. Okay. And I have poles at s is equal to -1 and -2, -3, and -4. Okay, so this is -1, -2, -3, and -4. And I know that when k is equal to 0, the start point of the root locus will be the open loop poles. The end point of the root locus will be either open loop zeros, so some of the poles we're going to go there, or they will follow the asymptotes, or they will either go to the infinity. That was the first, okay? So root locus starts at the open loop poles when k is equal to 0, and root locus ends at open loop zeros or infinity as k goes to infinity. Okay. And the second thing that I would like to sketch is the part of the real axis that is included on the root locus, okay? And we said that a point on the real axis is included in the root locus if the number of open loop poles and open loop zeros to the right-hand side of that test point is an odd number, okay? So I would like to ask you right now, if I pick a test point over here, will that be included in the root locus? No, because to the right of it, I have 0 open loop poles or zeros, so it will not satisfy the angle condition, therefore it's not included in the root locus. How about a test point over there? So I have 1, 0 to the right of this test point, therefore this segment of the real axis is included in the root locus, okay? So this is included in the root locus, okay? If I pick a test point on the real axis somewhere between -2 and -1, I will have 1 pole and 1 0 to the right of it, which is an even number. Therefore, this is not included in our root locus. Okay. If I pick a test point between -3 and -2, I will have 2 poles and 1 zeros to the right-hand side of that test point. Therefore, this segment, all the points between -3 and -2, on the real axis is included in our root locus, okay? And similarly, if I pick a test point over here, I will have 1, 2, 3 poles and 1 zeros, so there will be 4 poles or open loop poles or zeros to the right-hand side of it. Therefore, the section between -4 and -3 is not included. And if I pick a test point that is less than -4, then I will have 1, 2, 3, 4 poles and 1 zeros, which will be 5 open loop poles or zeros to the right-hand side of it. Therefore, this section is going to be included in the root locus. Okay. So I also see that we said that the root locus starts at the open loop poles and the root locus ends up at the open loop 0. So I see that one of these poles is going to the open loop 0 over here, which is located as s is equal to 0. Okay. And I understand that I conclude that the other remaining 3, since there are no zeros for them, they will follow the asymptotes. They will go to infinity. Okay. So what are the angle of the asymptotes? So we found them as pi over 2, 3, 2 pi over 3, etc. But where should I plot those asymptotes? I need to find the intersection of the asymptotes with the real axis, okay? And the intersection of the asymptotes with the real axis is -10 over 3 in our example. So it is somewhere over here, it's like 3.3. So it is somewhere over here is the intersection of asymptotes. And I will have asymptotes with angle pi over 3, minus pi over 3, and pi, okay? So I will plot them. So it will be something like this, okay? The first asymptote, the second asymptote, minus pi over 3. I mean, it doesn't have to be second or third, it doesn't matter, so on. And another asymptote has angle pi, so this will go to minus infinity on the real line, okay? And I know that the poles are going to, this remaining 3 poles are going to follow the asymptotes, okay? So, and I see that the pole at -4, if we increase k to infinity, it will follow the third asymptote over here, okay? And the other 2 poles are going to start at the open pole locations at -2.
Hocam,
n minus 2. I will finish this in a second and I will get your questions. All right? Okay. So they will start at -3 and -2. They will move towards each other. Okay. So they will get closer, just like our first example. Remember the second order example. At a certain stage, I will have double roots and they will break away and they will follow the asymptotes. Okay. So they will go towards each other. And then they will follow the asymptotes symmetrically. I couldn't plot symmetrically, but I'm sure we can plot better. So those guys will follow the asymptotes as s goes to k goes to infinity. Yes, I can take your questions right now.
Şey diyecektim hocam, bu aşağıdaki açı yanlış mı diyecektim ama değilmiş. O
Minus pi over 3.
devamıymış. Pardon.
Exactly. So this is pi over 3. And the other one was minus pi over 3. Okay, so this is minus pi over 3. So the angle of the first asymptote was pi over 3. Okay, and I add another 2 pi over 3. To pi over 3, I will have the asymptote with angle pi. And if I add another 2 pi over 3, I will have the asymptote with angle minus pi over 3. Okay. So far, so good. I think it's very, very intuitive in the sense that, for example, I see that if I increase at the beginning of this, when k has small values, the system seems to be stable, right? All the closed poles seems to be remaining at the open left half plane. But at a certain stage, when I increase k further, and further, two of the poles are getting bigger and they're trying to follow these asymptotes. And when they're trying to follow that asymptotes, they also pass to the right half plane. Okay, so if at a certain stage, if I increase k from a specific value and further, the system will become unstable.
Hocam zeros ve poles'lar şeye dahil mi? Root Locus'a?
Yes, so when k is equal to 0, we have the k is equal to 0, when we have d of s is equal to 0, right? So we have the open poles as the closed poles, right?
Teşekkürler.
And zeros is more questionable because then k has to be infinity. Okay, so zeros maybe not included for practical systems. It's not included, but points close to that zero are included. By the way, remember that this was let's inspect our very first example when we have two poles, okay, and on no zeros, right? Then we have two asymptotes. One of them is like a pi over 2. The other one is like minus pi over 2. And these roots began at s is equal to 0 with the open pole locations s is equal to -2. And they moved towards each other. We found that analytically by finding the root locations exactly. Okay. And then they at -1 they met and then become complex conjugate poles. They followed the asymptotes over here. So that was the case here. And in our second example, we have 4 poles, 1 zeros, okay? So root locus starts at the open loop poles, ends at the open loop zeros or the asymptotes. And there's only 1 0 here, so there's only 1 pole that can reach the 0, okay? The remaining 3 poles will follow the asymptotes, and the asymptotes has the angle as found here, and the intersection of the asymptotes with the real axis is given with this formula. By the way, we can drive this formula as well, but it takes about 1 lecture hour. So if you are curious about it, so just reach me, we can drive together at a later stage, but it's not critical how to find this point. But again, you will make a similar approximation, just like we did for the asymptotes here to find that centroid point. So it's not very difficult, but it takes some time. Any other questions? So I will give a break, but before the break, I would like to tell what we are going to do next. Okay, so what we are going to do next is that for a complete root locus, I need to find these critical points. What are the critical points here, by the way? Here are my closed poles. When I increase in k, these closed poles are following these lines. Where is the most critical point? So the most critical point are the points where we intersect the imaginary axis, right? Because at those points, the closed poles are going from left half plane to right half plane, or right half plane to left half plane, right? So the stability of the system changes around these points if you increase k further. Okay, so we will, after the break, we will find the intersection of the root locus. Intersection of the root locus with imaginary axis. Root locus with imaginary axis. Okay, and we will also find, one of your friends said that, okay, where exactly these two poles meet and begins to break away. Okay, so we will call these points break away and break in points, and we will see how to find them, to find this double root location, how we can find that. Okay, let me write that as, let me get rid of that dot over here first. We will find the break away and break in points next. Okay, but before that, let us give a 10 minutes break and then we can continue. All right?
All right.
Right. So see you in 10 minutes then.